Hello and welcome to a new K-Steve math video. This math video is going to be a getting ready for pre-calculus video. A couple years ago I did one for pre-algebra, algebra 1, geometry, and algebra 2, but I ran out of time / whatever, life happens. So I want to pick back up and go ahead and do one for pre-calculus and maybe also for calculus, probably for calculus as well. So I have some problems here that a math teacher who I am somewhat associated with has created for their students to use in the summer to review concepts from Algebra 1, Geometry, and Algebra 2 before they start pre-calculus. So I did not create this, but I'm using this as a tool, and I hope that you'll get some benefit out of it. So let's just go ahead and start right off. Number 1 here says simplify the given algebraic expression. And so we are going to look at this and say, I see some distributive property, and then I might have some like terms to add together. So hopefully, since this is kind of harking back to algebra 1 or even pre-algebra, hopefully this one's pretty easy to do. So definitely feel free to skip around if you want to get to like harder stuff that you have more trouble remembering. So 7 times 4y gives us 28y, and 7 times -8 gives us -32, and then this negative needs to be distributed, so it's like multiplying by -1. -1 times 3y is -3y, and -1 times 3 is -3, and now we add our like terms. So 28y minus 3y is 25y, and -32 minus 3 is -35, and that's our answer. This next one, it has the same kind of instructions, but looks a little bit more complicated. So we have to know what our order of operations are, right? That we always start with parentheses, or brackets are included in the same like step as parentheses. But since there's more than one, we have to go like the most inside. So like I'm gonna look inside this bracket and do what's in the bracket first, but inside of the bracket is a parentheses. So that parentheses is what we need to take care of first. Although it's kind of weird whenever we have algebraic expressions like this, dealing with this parentheses, there's not actually anything inside to do. So it's actually that I want to get rid of the parentheses by multiplying first and then go from there. So everything else is going to stay the same. So 13x squared plus 5 minus, and we're going to do 4 times x squared is 4x squared, 4 times -6 is -24, and then we've still got this plus 6 right here. And then we say, okay, what else can I do inside of these brackets? Now I can add -24 and 6 together. So that's gonna give me all the same stuff in front, but we're gonna do -24 plus 6 and get -18. So this will be 4x squared minus 18. And then this negative in front of our bracket is like a -1 that we'll need to distribute. And then we'll check to see if there's any like terms. So 13x squared and plus 5 stay the same. If those had been like terms, we could have added them at any point along the way, but they're not, so that's why they've just hung out outside of our bracket. So it changes both of these signs, and we add our x squareds together to get 9x squared, and we do 5 plus 18 and get 23. So that would be our answer. Okay, looks like we've got some exponent review here. So simplify the following expression, 5 to the -5. So a friendly reminder, negative exponents are telling us that we have a fraction. So if this was 5 to the +5, we'd multiply out 5 times, and that'd be our answer. But 5 to the -5 means that it's actually 1 over 5 to the +5. We take our negative exponents and we move whatever has that negative exponent, we move it down to the bottom of the fraction, and that turns it into a positive. Now I don't know what 5 to the +5 is. I know that 5 to the 4th power is 625, and I know that because that's 25 times 25, which I like, that is 625. Alright, evaluate the given exponential expression. I don't want to. This is actually kind of a similar thing here. So what we do with these exponents right here, we have a power to a power. We can actually simplify this by saying this is 4 to the 12th. And 4 to the 12th is going to be a really big number, and it's going to be a number that I don't really want to find out by hand. So 4 to the 12th is apparently 16,777,216. Now, how would we figure that out without looking at the answer key? We could multiply 4 out 12 times, or we could use our calculator. I think anything above like anything above like going to the 5th power, for sure, I'd hope that you'd be able to use a calculator for, because it gets really, really frustrating to do that by hand. Okay, simplify the exponential expression, which you may have seen the answer a second ago, so just pretend like you didn't. So when we're simplifying exponential expressions, we kind of take these as on this problem, 3 different things that we're trying to do. First, we're trying to take our normal numbers, -7 and -3, and say, okay, we're multiplying them together. What does -7 times -3 multiply to get? And the answer to that would be 21. And then we look at the x's and we say, okay, I've got an x to the 5th and an x to the 7th. What can I make those be together? And this is where we add our exponents, because if I have x to the 5th, we're saying we have x 5 times. If I have x to the 7th, I have x 7 times. And so together, that means I have 5 plus 7, which is 12. And I do the same thing with the y's. Y to the 1st and y to the 4th together mean that I have 5 y's, so this would be y to the 5th. So in number 4, where we had a power to a power, that's multiplication to combine those exponents. But on 5, where we have them next to each other, and we're saying I have x to this and x to this, and I want to combine them, that's where we add. On 6, where we've got a fraction, we're going to end up using subtraction. So there's actually numerous ways that we could go about 6 as far as the order goes, but we should all end up with the same answer at the end, mostly because it says use positive exponents only. If that wasn't there and we were allowed to leave things with negative exponents, our answers could look different. But that's one of the reasons I think that instruction is so common, is to make it easier to tell that we all have the same thing. Is if we all have to have positive exponents, then all of our answers should look the same. So we could take care of this 3 on the outside right away, or we could try to simplify what's on the inside first and then deal with the 3. And that's what I lean towards, is that second option of saying, okay, what can I do inside with this fraction? I can simplify the -14 over 7 and get -2. I can simplify the a squared and a to the 7th. So this is where we subtract our exponents, because one's on top and one's on bottom. Or if you want to think of it like they're canceling each other out, if I have an a squared and an a to the 7th, that a squared goes away completely and takes 2 of the a's away from the a to the 7th and leaves a to the 5th on bottom. So we have a to the 5th on bottom. It's a little trickier with negative exponents. You either can think 6 minus -5, which is really 6 plus 5, or you can go ahead and say, I'm going to move this b to the -5 up to the top to give it a positive exponent, and then think about how they combine. Whichever way you do it, you should get a b to the 11th on the top. And now we're ready to deal with that third power. So when we have more than one thing on the inside of our parentheses and an exponent on the outside like this, everything inside gets that exponent. Now, if there was a addition or subtraction symbol in this, like if it was -2 plus b to the 11th or -2 minus b to the 11th, this problem would be totally different. It matters that all that's really happening here is multiplication and division. So that's why everything is going to get cubed. So we need to cube the -2, which will give us a -8. We need to cube b to the 11th, and so that's multiplying the exponents together and getting b to the 33rd. And we need to cube a to the 5th, so 5 times 3 is 15. And we can't combine the a's and the b's. They're not like terms, they're not like bases, so they have to stay separate. The -8 still has to be there. And it's okay that we have a negative in general, because that -8 is not an exponent. So you don't you don't get to move like 8 down to the bottom and make it positive, because the negative is saying that it's a negative 8, not that it has a negative exponent. Negative 8 actually has an exponent of 1 because it doesn't have an exponent. So keep that in mind as you're working through this, that numbers have like kind of, it almost feels like they have different rules in a way than our variables do with exponents. But really it's because we just usually figure out what negative 2 to the third power is instead of leaving it as negative 2 to the third power. So anyway, let's look at 7. Use the product rule to simplify the following expression. And you may not realize what the product rule is as you're doing this, but however you've learned to simplify radicals, the idea is saying, what can I split these up into that have perfect squares? For instance, 18 is really 9 times 2. It's also 6 times 3, but 6 and 3 aren't perfect squares. If I change 18 to 9 times 2, then I can say, okay, let me separate this out. And x squared actually is also a perfect squared, so I can separate that out as well. That's what the product rule says, is that these things that are inside, since all of it's multiplication, I can split it up into separate radicals, because I know that square root of 9 is 3, and I know that square root of x squared is x. Either thinking that square roots and squares cancel each other out so we get x, or thinking, okay, what's the thing that multiplies together to get x squared that's the same? X and x, so the square root of x squared is x. But we do still have a square root of 2 that did not get to come out of the radical. So our answer is 3x square roots of 2. This one says use the quotient rule to simplify, and it says assume that x is greater than 0. When you see things like this, it's a mathematician being particular with this problem and wanting to make sure you know that they are not trying to divide by 0. So because there's an x on the bottom, if x did happen to be 0, this problem would not work. And in these types of problems, we very rarely know what x is supposed to be. It's just an exercise in making sure you know how to simplify. And so this is just kind of overkill of saying, no, I'm not trying to divide by 0. So the quotient rule is similar to the product rule, because in both of these rules, like, we can switch what is in the same radical and what is in different radicals. So here, these are in different radicals, but we actually could write them all in the same radical, like this, which is helpful because then it might be easier to see that we can actually simplify these by dividing. Hopefully 4 goes into 256, and then we've got a smaller number to try to simplify. X does go into x cubed, and leaves us with x squared. 256 divided by 4 would be 64. And these are both things that square root, so it would be 8x, and that'd be our answer. Number 9, subtract the following terms if possible. So when we're adding or subtracting radicals, we need like terms, or like radicals. So you can do square root of 2 plus square root of 2. You can't do square root of 2 plus square root of 3. It feels very much the same as when we try to add x's together or y's together. So these are not like radicals because we have a square root of 75x and a square root of 27x. But let's simplify them and see if we end up with something that's the same. So for 75, we want to split this up into 25 and 3. I can square root 25 and get 5. And that leaves me with 3 and x on the inside because the x is just by itself. It doesn't have anything to it's not x squared or bigger, so there's no x's that get to move out. And then 27 is 9 times 3, so square root of 9 is 3, and on the inside we'd have 3x again, which is nice because otherwise we would have simplified for nothing if these didn't actually subtract. So this actually says to pick A or B. So we would pick A because we can actually simplify this. We'd say 5 minus 3 is 2, so I have 2 square roots of 3x, and that would be my answer. So to rationalize the denominator, we're going to multiply by something on bottom that gets rid of the square root. So since this is square root of 11, if I multiply by square root of 11, that's going to get rid of that square root. Because square root of 11 times square root of 11 is square root of 121, and the square root of 121 is 11. If you multiply square root times itself, you just get what's inside the square root. So that means I'll have 11 on the bottom. On the top, square root of 5 times square root of 11 is square root of 55, which doesn't simplify because it's 5 times 11, and neither of those are perfect squares. So this is our answer. You'll see this term a lot. You may already have in math, but in pre-calculus and above it happens, even more so. It says to have an exact answer using radicals is needed. So this is an exact answer because if I type it in the calculator, it gives me a decimal and I have to round, and that's less exact than what this is. So saying square root of 55 over 11 may feel less exact to you than having a decimal because it's hard to picture what square root of 55 over 11 is. But as far as the math world goes, we want to keep things as fractions and radicals as much as possible so that whenever we do hand off our answer to an engineer or architect or builder or whoever it might be, we hand it over with a decimal at the very last moment, or let them decide when they need the decimal, so that we've done as little rounding as possible. Because if you round at every step of a problem, you are potentially introducing more and more error into your answer. So we just like to save it for the very last possible step, if we even bother rounding at all. Rationalize the denominator again, but now we've got two things. So we have to multiply this by its conjugate, its complex conjugate. And so what that means is that whatever this is, this is like a two-term, so kind of like a binomial, although there's not x's, so I don't think we actually can call it a binomial. There's two terms here. It's a complex number. We want to multiply it by its conjugate, which means we want to multiply by square root of 5 plus 2 on the top and the bottom, like this. So for the top, that means distributing. For the bottom, that means foiling. But when we FOIL it on bottom, the whole point of this is getting rid of the square root on bottom. It should actually cancel out our radicals. So we do square root of 5 times square root of 5 and get 5. Square root of 5 and 2 gives us 2 square roots of 5. Negative 2 times square root of 5 gives us negative 2 square roots of 5. So see, those are canceling. And then negative 2 times 2 gives us negative 4. So we do 5 minus 4, which is 1. That worked out super conveniently because that means that our answer is 11 square roots of 5 plus 22. Evaluate the given expression. This is a third root. So square roots, you're looking for pairs of numbers. Cubed roots, you're looking for trios of numbers. And we could continue that pattern on with fourth roots and fifth roots and so on. So our big question here is going to be, is there something that multiplies together 3 times to get 216? And we could start off just by making a factor tree and have that help us. This would be 2 and 108, 2 and 54, 2 and 27. So we've already got 3 2's, so that's something that simplifies. And 27 is 3 and 9, 3 and 3. And you might have realized that 27 had a cube root. And you might even have realized that 216 had a cube root, depending on your mental math skills. I actually knew from the beginning that the cubed root of 216 is 6. So that's what we're getting here because we have 3 2's and 3 3's. We put a 2 and a 3 on the outside, which together makes 6. But a couple other things are happening here. This is on the bottom of the fraction, so it's not that we get 6. We get 1/6, and we've got a negative. For square roots, that wouldn't give us a real answer, but for cubed roots, it can, because you can multiply together 3 negative numbers and get a negative number. Right? So if I do negative 1/6 times negative 1/6 times negative 1/6, I get negative 216. So that's my answer, is negative 1/6. Here we've got a rational exponent. So it says to not use a calculator, but this is a relatively small number, so hopefully that's not too hard to do. When we see a rational exponent, the top number is giving us our power, the bottom number is telling us our root. So we're rewriting this expression using a radical. It's the cubed root of 125. You can either put a squared here on the inside with 125, or you could make a big set of parentheses around it and say that the squared is on the outside. We're allowed to do this actually in either order. Since we're having to do this by hand, we would actually want to cube root first and then square, because cube rooting makes the number smaller and easier to square. The cube root of 125 is 5, because if you do 5 times 5 times 5, you get 125. And if you're struggling with cubed roots, just know that cube roots are going to get big even faster than, cubes are going to get big even faster than squares do. So the fact that we have 125, and that's actually kind of a big number, we still should be looking at small numbers for our cube root. So the cube root of 125 is 5, and then we square the 5 and get 25 for our answer. What do we have next? Some polynomial operations. So these are polynomials. Anything with x's and numbers and addition and subtraction is considered a polynomial. There's actually probably a wider definition of that as well. But what we want to do is add like terms together. We have a plus here, so these two parentheses can just add together. This minus, though, we actually would be probably best off distributing this negative and then adding like terms. So we'd have a negative x squared and a positive x and a positive 3. And then I can look at all three of these and say, okay, what's my x squared? 7x squared plus 2x squared minus x squared. So that's 8x squared. It does say to write this in standard form. So we do want to start off with x squared and then look at x and then our number. Because that's the standard form, starts with biggest exponent and works its way down. So now I want to do my x's. Negative 6x, negative 3x, and plus x. So that's negative 9x plus x is negative 8x. And then I want to do just the numbers. So I'm going to do minus 1, plus 5, plus 3. So that's 4 plus 3 is 7. So my answer is 8x squared minus 8x plus 7. This says the degree of the resulting polynomial is. So degree is the biggest exponent we see. So this is a squared, is the biggest exponent. So our degree is 2. Find the product. X minus 2 to the third power. Now you're not just allowed, this is what I was talking about earlier. This is not the same as x cubed minus 2 cubed. That is not going to give you what you need. What we need to do is x minus 2 times x minus 2 times x minus 2. So we do this, we can't do this all at once. We have to do these two together first and then multiply our result by x minus 2. So this is foiling, right? X times x is x squared, that's our first. X times negative 2 is negative 2x. Negative 2 times x is negative 2x. Negative 2 times negative 2 is plus 4. So we get x squared minus 4x plus 4, and we're going to multiply that by x minus 2. So now we distribute the x through all three of these and then negative 2 through all these. Or you could do it the other way and distribute the first parentheses into the second, whichever one makes more sense to you. So I'm going to distribute this x and get x cubed minus 4x squared plus 4x, and then I'm going to distribute the negative 2. I'm going to write it underneath this so that, whoops, I skipped something. And I caught it because of how I'm writing it. So negative 2 times x squared, I'm going to write right here under this x squared. Negative 2 times negative 4x is plus 8x, and negative 2 times 4 is minus 8. Then we add our like terms together, and this is our answer. So we'd get x cubed minus 6x squared plus 12x minus 8. You may have learned how to use the binomial theorem and Pascal's triangle to figure out binomials to a power as well, which is great. I don't know that it's faster to do it that way on a problem like this where it's just to the third power, but certainly if we were to the fourth or fifth or sixth, that would be something we'd want to look at. And there's a decent chance that in pre-calculus you'll go over the binomial theorem again, depending on your school and how much time you have and whatnot. Let's look at 16. We have two products that we need to address first. So we're going to FOIL here and FOIL here, and then our results need to be subtracted. So if I FOIL 3x times 4x is 12x squared, 3x times negative 3 is negative 9x, negative 1 times 4x is negative 4x, and negative 1 times negative 3 is plus 3. So that's our first result. Our second result is 4x times 6x is 24x squared. 4x times negative 1 is negative 4x. Negative 5 times 6x is negative 30x. And negative 5 times negative 1 is plus 5. So we can add our like terms in the middle and then subtract, or you could just go ahead and subtract. I think it's a little bit less likely that you'll make a mistake if you go ahead and add like terms in the parentheses first. We also could rewrite this vertically, kind of like what we did before. Negative 4x minus 30x is negative 34x, so we switch it to plus 34x. And this switches to minus 5, and so our answer here is negative 12x squared plus 21x minus 2. That's our answer. Alright, now we've got quite a few factoring problems, which is good because reviewing factoring will be very helpful. And hopefully each of these is a little bit different because there are kind of different types of factoring problems. So for instance, x squared plus 12x plus 35, since there's nothing in front of x squared, all we do is come up with what multiplies together to get 35 that adds to get 12. And that's our answer. And there is something that works. If there wasn't anything that works, we'd say, oh, it's prime, can't factor it. But there is something that works. So think of the factors of 35. All of our choices are 1 and 35 or 5 and 7. 5 plus 7 is 12. So this would be x plus 5 and x plus 7. Or you can write that in the other direction, and that would also be a correct answer. Incidentally, I have an app on my website that will generate problems like this for you and show you the answers. So if this is something you'd like some extra practice on, I will have a thing pop up hopefully that has that link, or you can look in the description for that link, because this is one of those things where having the ability to practice can be super helpful. We've got another one here, and this one has a minus, which is going to affect us a little bit because we have to, instead of thinking about positive numbers that multiply to get 63, in order to multiply and get a positive 63, you actually need two negative numbers so that you can add to get negative 16. So we can still think about the factors of regular 63, but whenever we actually try to figure out what this is, we're going to add it together, but then think about the negative version of that, right? So 7 plus 9 is 16, but because I want it to be negative 16, they both need to be negative. It doesn't look like we have more that are simple ones like this, but there are situations where this might be a minus sign, and then what we're doing essentially is we're going to subtract our numbers to see what gives us the middle one. So like I said, I have an app that can help you practice that, where you can get some of each type and know if what you're doing seems correct or not, and link in the description. And 19 has something in front of our squared, and so this is trickier. There are a lot of different ways we can use to factor ones like these. You need to, if you have not already, You need to find a way that works for you and use it. It was not until I was a teacher that I even realized there was a way to do this other than guess and check. And I have no idea if that's just because I didn't pay attention in math class when my teacher gave us another way, or if it's that no one gave us a shortcut because they figured guess and check worked. I don't know. But guess and check works if you're willing to basically be wrong some of the time. So guess and check means that you'd put two parentheses and you would have to come up with, how can I split up 12y squared into these two spots, and how can I split up 10 into these two spots so that when I do the outside and the inside added together, it gives me that 3y that I want. And because 12 has actually a lot of factors for such a small number, that's going to be a tricky thing to do. And actually, this might be prime because all of these are pluses. So I think we'd need to be able to subtract to get something as small as 3. I feel really confident about that. But I do want to talk about a trick that I use now that I know about it to factor with things like this. And it's called slide and divide. So slide and divide, you take the number in front, 12, and you slide it to the 10. When we slide it, we multiply. So that would change this problem to y squared plus 3y plus 120. And then we look for factors of 120 that would add to give us 3. So that's not going to work. 120 is too big of a number. Its closest factors to each other, 10 and 12, obviously add up to be more than 3, right? So this is actually prime. But if it did work, and I did get something that I could put in these parentheses, then what we would have to do is divide by what we slid earlier. I also have practice problems for these in a video of, I actually have a video of using the box method to do this type of problem. I've also got a video of using slide and divide to do this type of problem, and I'll put those links in the description, because if you've been before now basically hoping that factoring will go away and you won't have to worry about it, that's not the case. Like, it's going to sneak up on you and you're just going to all of a sudden have a problem that needs to factor. And so if you don't remember how to factor, it's going to be a problem. But this one does not factor its prime because it doesn't work to try to get such a small number in the middle when we're not allowed to make one of our numbers negative. My favorite type of factoring, I like all factoring actually, because I'm one of those people. I'm good at it, so I like it. So factoring with 4 terms, we're looking to try to factor by grouping. And so what we do is we group the first 2 numbers and the last 2 numbers, or terms, whatever you want to call it, and we factor out the greatest common factor just from those groups. So x cubed minus 5x squared has x squared in common, which leaves us with x minus 5. And then it's almost like a completely separate problem. I want to say, what does negative 9x plus 45 have in common? Negative 9. And that would also give us x minus 5. And that's the whole point of factoring by grouping. If you don't get the parentheses to be the same thing, either you made a mistake or it was not actually factorable. One of those two things. But since they are both x minus 5, we factor the thing they have in common out, x minus 5, and then in another set of parentheses we write what's left over. And I actually just realized as I was about to write this in the answer blank, x squared minus 9 actually factors as well. And this, again, like, you're going to need to remember these factoring things. This one in particular creeps up a lot. X squared minus 9 is the difference of 2 squares, which means that we can split it up into, I don't know what that plus sign was. Hang on, let's try this again. So x squared minus 9 factors into x plus 3 and x minus 3. This is a pattern that's really helpful to just have memorized. You're looking for anytime you have 2 terms that are being subtracted where you can square root both of the terms. It lets you split them up into 2 parentheses where one has a plus and one has a minus. And otherwise the terms are the sum and difference of what we got when we square rooted x squared and 9. It does not work if it's x squared plus 9. That would not actually factor anymore. But since it was minus 9, it did. So this would be our correct answer. X minus 5, x plus 3, x minus 3. And those, again, can be in any order. 21. Factor completely or state that the polynomial is prime. This is a weird one, and one that I don't think this process comes up a ton, which is going to be a bright side, because I think that I actually am redoing this problem because the first time I had a mistake and then just it didn't work well. So anytime I have to basically stop and figure out a problem as a math teacher, it's like, okay, I don't think that you're going to be expected to do this on your own, or at least not very often. So we look at this and hopefully we notice, hey, these all have a 2 in common, these all have an x in common, so let's take out the 2x. That leaves us with x squared minus 64a squared plus 14x plus 49. Okay, so we took out the 2x that's in common, and now what's inside of this actually is a little weird. If it just was x squared plus 14x plus 49, that is something that I can factor. Or if it was just x squared and this minus 64a squared, that's actually something I know how to factor as well. But because it's both of those, it's a little trickier. So let's think about what x squared minus 64a squared would factor into. That's a difference of 2 squared, so we could do x minus 8a and x plus 8a. And that would be an answer for that. If it was x squared plus 14x plus 49, then we would factor this into x plus 7 and x plus 7. So I think the idea here is, would it be true to say that this factors into x plus 7 minus 8a times x plus 7? Oh, I did not mean to close the parentheses there. Plus 8a. Oh, I think I ran off the screen. There we go. So how would I know if this is actually how this works out? Well, we could go through and kind of think about the multiplication happening. X times x is x squared, x times 7 is 7x, x times 8a gives us 8ax, and then think through 7 multiplied through and negative 8 all the way through, and I'm pretty sure this is what it works out to be. Now, as far as you being like, how would I know that that's how it works? I'm going to be honest, this is not something that I normally teach people how to do, so I'm kind of at a loss off the top of my head. This might be something that I actually investigate afterwards, so that I can figure out what exactly is going on here. Because I said I was good at factoring, and I want to still be good at factoring. But like I said, this is not, I think, something that happens a ton to us. So hopefully, if you don't fully understand what happened here, that actually should be fine, I think. I'm gonna double check my answer. Yep, that's what it is. So it is neat to me that that works out that way, but it's not something that I feel like happens to us a lot. All right, new sets of problems here that are a little bit different. Here we have rational expressions, which means that we have algebraic expressions that are in the form of a fraction. And so the tricky thing with fractions that have x's is that if there's an x on the bottom, you got to be careful, because we are not able to divide by 0. It doesn't make sense as a question. 5 divided by 0, you can't do it, and it just doesn't even make sense whenever you're being asked to do it. That if you have 5 cookies and you want to divide those 5 cookies up amongst your 0 friends, that doesn't make any sense to divide into 0 groups. So on 22 here, I'm going to simplify the rational expression, and then it also wants us to find all the numbers that must be excluded from the domain of the simplified rational expression in order for it to be equivalent to the original expression. So what happens here is if we factor this on top and bottom, we will get an idea of where the top could equal 0 and where the bottom could equal 0 really easily. So on top they have a 5 in common, and that gives us x minus 4 inside our parentheses. On the bottom, we say what multiplies together to get 16 that adds to get negative 8. So that's x minus 4 and x minus 4. And then what happens here is that we can cancel out the x minus 4 on top and bottom, but that's how we would simplify this. But we have an issue because in our original problem, and actually also in this new problem as well, we're not allowed to plug in 4. So that this is actually kind of a weird problem, and it's making me a little nervous about how correct I am, because normally we would have 2 different parentheses down here on the bottom. One would cancel, and so whatever's left would still be there and would be a different value that doesn't work. But here, the number we canceled out, or the value that we canceled out for, is an issue before we canceled and after we canceled. So definitely x cannot equal 4. But that's the only number that it can't be equal to, because that's the only number that when we plug it in for x is going to give us 0 in the denominator, 23. And it looks like this is a similar problem, so hopefully this will lend itself a little better to the explanation I was planning to have to give on the last one. Okay, so we want to factor the top and bottom. So we need to say what multiplies to get negative 9 that adds to get 8, which would be a plus 9 and a minus 1. Because those add to get positive 8, but multiply to get negative 9. I'm going to do the same sort of thing on the bottom. What multiplies to get 54 and adds to get 15, which is 6 and 9. Okay, so what's happening here is we have a common factor, y plus 9 and y plus 9. So those go away when we simplify, so that we get y minus 1 over y plus 6. But even though we canceled out the y plus 9, the number that when we plug in gives us 0 for y plus 9 is still an issue. If you look at the graph of what we originally have with this y squared plus 8y minus 9 over blah 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 blah, if you look at that graph and then you also look at the graph of y minus 1 over y plus 6, they will look identical. But if we were to zoom in on negative 9, and I say negative 9 because of what we canceled out, what makes that equal 0. If we zoom in on negative 9, for our original expression, we'll have an undefined value at negative 9. Whereas where we canceled it out and wrote a new expression, we do get a value there. So the whole point of, or part of the point of this problem is recognizing that, yes, negative 6 is an issue, because even after we cancel things out, if I plug in negative 6 on the bottom, I'm going to get a 0 on bottom, and that's not okay. But even though we canceled out the 1 plus 9, negative 9 is still something that has to be excluded from our domain in order for us to actually be talking about the same expression. So there are 2 values here, negative 6 and negative 9, that both of these actually are excluded from our domain. Alright, let's do some adding of rational expressions. Rational expressions tend to be something that a lot of people don't like because there's a lot of factoring and there's a lot of fractions, and those are 2 things that lots of people don't like. So keep that in mind, that I know that that's a thing. I'm going to factor this first fractions denominator in the hopes that there will be something that I can make them both equal, both denominators equal, without just having to straight up multiply each other by the other denominator. So x squared plus 8x plus 16 is x plus 4 times x plus 4, which means that I can multiply the second fraction by x plus 4 on top and bottom, and now I will have common denominators. So that does require us to distribute this 4, and all of this is going to be on the top of our fraction now. And on the bottom we'll have x plus 4 times x plus 4, which we could write as x plus 4 squared. And if we would want to add the 16s together and get 32. And I've not been paying attention to the answer blanks down here. So the question here is, do we need to exclude anything from our denominator? Like in the previous examples where we had to look at where the bottom equals 0. So if I make x plus 4 squared equals 0, well, the squared can just go away. I can square root both sides and I'd still have 0 on the right. So then it becomes, where does x plus 4 equal 0? Which would be at -4. So there is a number that we need to exclude. So we'd pick this first option. And we could actually factor out this 4 in common on top. The benefit to that would be us being able to tell for sure that nothing cancels here, because if something did cancel, we would want to simplify this just like we always simplify fractions. But it's x plus 8 and x plus 4, and those are not the same, so they will not cancel out. Ooh, a good old linear equation. I feel like I'm back in Algebra 1. How about you? So we need to distribute, actually on both sides. And then get our x's on one side and our numbers on the other. So subtract 4x over here, which that's nice. That's just going to give us an x. And then we've got -10 plus 8 is 8. I'm going to subtract that 8 over to this side and get 8. So which of these is true? The solution set is the number 8. So the way solution sets work is you use these fancy brackets around any numbers that are a part of the answer, with commas separating them if there's more than one. So if we'd gotten 2 answers, we'd have 8 and then a comma and then whatever our other answer is. The part B, the solution set, is x, where x is a real number, is just saying, that would be if we ended up with something that the variable canceled out and we got like 0 equals 0. That would mean that you could literally plug in anything you wanted to and get the equation to work. So things like, if we have an equation like 2x plus 1 equals 2x plus 1, it's a really boring equation, but that equation is true for every single number that you can think of, because you pick a number like 5, you put it in both places, and it's going to give you the same thing on both sides. Then C, that circle with a line through it, is called the empty set. And this is another way of saying no solution. So that would happen if we had 2x plus 1 equals 2x plus 5. Well, there's no way for you to get the same number on each side when you plug it in. You can't get the same thing because one of them has a 1 and one of them has a 5. So this seems kind of random, because look, this one is I guess this is just a set of solving equations, because now we've got a rational equation. Right, write the value or values of the variable that make a denominator 0. So it looks to me like we've got -2 for the first denominator and +2 for the second denominator. And actually we have both of those repeated again once we factor the last denominator. So those are the things that we're going to exclude. And one of the reasons we do excluded numbers like this is because now I'm going to solve this. And if I happen to get an answer of -2 or 2, that means it's not really an answer. We call them extraneous. There we go. It's been a while since I've used that word. We call them extraneous solutions, which it really just feels like somebody went really big on the word extra. We call them extraneous solutions. There is a thing that we do in the process of solving a rational equation like this, where we multiply by things with x in them. So the way I'm going to do this is I'm going to say, okay, I need an x minus 2 on this first one. So I'm going to put an x minus 2 on top. I need an x plus 2 here to get my common denominator. So I multiply by x plus 2 here. That's not actually something that is completely mathematically sound. It is the best we can do. It actually works pretty well. But because we're multiplying the top and the bottom here by x, we are potentially introducing in what could be an extra solution. And so that's why we care about these excluded values, because if we just so happen to have introduced 2 or negative 2 as a solution, those aren't really supposed to be solutions. So let's go ahead and work this out and see what happens. We need to distribute this 5. And we need to distribute a negative 1. And then this 3x doesn't change because it already had its common denominator. Now we could put all of this over x minus 2 times x plus 2, our common denominator, but this really cool thing happens in rational equations, where if all your denominators are the same, you no longer need your denominators. You can just forget about them, but they all have to be the exact same denominator. And that's also true if you're just making everything be over 4 and there's not an x involved in the denominator at all. You don't have to keep the fractions in an equation if you're willing to get common denominators for everything. So now let's solve. 5x minus 1x is 4x. Negative 10 minus 2 is negative 12. So I'm going to subtract the 4x over to the right side, which gives me a negative 1x. Divide by negative 1, and I get x equals positive 12. So that is my solution, 12. I think it's pretty unlikely that you would come across one of these that would be all real numbers. I guess it's not super unusual, but I feel like you, as a teacher, you'd have to work pretty hard to come up with one that gave you all real numbers. But the no solution would happen potentially either if there just is no solution to the equation for some reason, or if we got a solution but then it was one of our excluded values, and so then it wouldn't really be a solution, so we would say no solution. There are also ways that you could end up with, hey, my method gave me 2 solutions, but one of them isn't really a solution, so I still have one. That wouldn't be no solution. You'd just say what the one solution is that is really a solution. Absolute value equation. So for absolute value, you make sure the absolute value is by itself on its side of the equation, like it is right now, and then you separate this into 2 questions, because we can take the absolute value of a positive 3 and get positive 3, or it could be that we take the absolute value of a negative 3, and that would also give us 3. So we separate this into the 2 cases that could have happened to us, and then we solve them. So we should get 2 answers. So 2x equals 4. We divide both sides by 2 and get 2. And then we add 1 and get negative 2, so divide by 2. And we get negative 1. So we have 2 answers this time, 2 and negative 1. And we just write them in that set of curly brackets with a comma in between, because we're making a list, basically, of the things. And if this looks like a point, just keep in mind that points have parentheses. This has squiggly brackets, and that's, totally different. Squiggly brackets are talking about, hey, this is a set of numbers that I'm talking about. Parentheses, we're either going to be talking about points or intervals. Okay, we are going to solve this equation. It has a squared for one of its x's, and then it has a regular x. So this is a quadratic equation, since the highest power is 2. Because it does not have like a plus 5 or something like that, I'm going to do this a little bit differently than I would if it ended up with 3 terms. I am still going to start with the first step as normal, which is to get everything on the same side. So I'm going to subtract 54x over to the left side. In general, it's easier to work with if your x squared term is a positive term versus a negative term. So if you're trying to decide which direction to move things, that is one way to guide yourself. We could plug this into the quadratic equation. That is your always works method for quadratic equations. I don't know if I said it right. Quadratic formula. We could always use the quadratic formula because this is a quadratic equation. But if we can factor this, if we can factor this, we can get our answers a lot quicker, maybe with less mistakes or less potential for mistakes. So to factor this, I would factor out the greatest common factor since there's only two terms. So they both actually can be divided by 3x, which would leave us with x minus 18. Because 54 divided by 3 is 18. And so now, to finish solving this, we separate it out into two questions. Where does 3x equal 0? And where does x minus 18 equal 0? Well, we can go through the steps to actually solve these and see what the answers are. Or it may be that you can look at them and see what the answers are. That 3 times what equals 0 has to be 0. And what minus 18 has to be, or has to give us 0, that has to be positive 18. So 0 and 18 are our two answers for this quadratic equation. 29 says to solve this by completing the square. Completing the square is something that you may or may not like, but it is something you're going to use in pre-calculus in a way that is different from how we are using it here and how we learned about it in Algebra 2, because if we're being perfectly honest with ourselves, if I were to choose how I wanted to do this problem, completing the square would not be my first choice. In fact, very rarely would I choose to complete the square over factoring. Actually, I'd never do it. I'd never complete the square instead of factoring if I knew something was factorable. But it's not super likely that I'd try to complete the square instead of using the quadratic formula, personally. So we, in pre-calculus, will actually do some things where you do in fact have to complete the square, and there's not some other option. And so that's why we practice with quadratic equations, because it gives us a feel for how the process works that is a little bit easier, I think, to understand than if we just jumped right in with what we're doing in pre-calculus. And you may have seen some of it actually in Algebra 2. If you did conic sections in Algebra 2, then you may have done some completing the square already in that context. So here's how we complete the square. You'll notice I rewrote this with blanks on each side. We want to come up with a number that whenever I add it on the left side into this blank, it allows me to rewrite this as x plus something squared. So we're trying to figure out what number could I put there so that I could factor this into the same parentheses twice. And it may be that that's something that you can think through pretty easily, or it may be something that is like a huge struggle to think through. What we want to do is, if it is a struggle, there's a really cool mnemonic device kind of thing that I have for you, where we just do the same thing every time. We take the number in front of x, we half it, and we square it. Now, this method was brought to us by good old Professor Hoffensquared, who's a German professor. And so he says, you got to half it, and then you got to square it. So the method was named after him, Hoffensquared. So 4 divided by 2 is 2, and 2 squared is 4. So we need to put a plus 4 here, and a plus 4 here. We factor x squared plus 4x plus 4 into the things that multiply together to get 4 and add to get 4, which is 2. And then we go ahead and add the things together on the right side. So that would be a 1. Now we can square root both sides to get rid of that squared, so that we get x plus 2 equals 1, but with a plus or minus, because anytime we square root in an equation, we need to put a plus or minus. We subtract 2, which is not just going to give us plus or minus 1 again. Like, you need to do 1 minus 2 and negative 1 minus 2, which are not the same number. This would be negative 1, and this would be negative 3. So those are our two answers, negative 1 and negative 3. We could have done the same thing by getting everything to one side and factoring, or we could have used the quadratic formula, but we completed the square. That's the process right there. All right, solve the quadratic equation by completing the square, and this time we cannot factor. This time our answers are not going to be so nice, and I know it can't factor because I just tried to in my head real quick. So if we weren't being forced to use completing the square, we would use the quadratic formula, sorry. It is a quadratic equation. We would use the quadratic formula, but it says complete the square, so that's what we're going to do. when we complete the square, we start by moving the number over to the other side. And then I take that opportunity to write a blank here and a blank here and part of that is to help remind me what it is I'm trying to do. I'm trying to put in a number that will complete the square. So, like I said last time, we're trying to come up with what number I could put here, so when I factor, I get x plus something with the squared on the outside. So Professor Hoffman's square tells us to half the number and square it. So half of 8 is 4, and 4 squared is 16. And so I add 16 to both sides, and then continue on. So what multiplies to get 16 and adds to get 8 is 4 and 4. Incidentally, that's also always going to be, that number right there is always going to be what you get when you half it before you square it, which is convenient when you have like fractions involved so that you don't have to think as hard about the factoring. Negative 6 plus 16 is 10. I'm going to square root both sides, and there is not like a perfect square, or 10 is not a perfect square. That's what I'm trying to say. And so, and it doesn't even have anything that can simplify about it, because it's just 2 times 5. So we would put a plus or minus sign, and then we'd leave it as square root of 10. We subtract the 4 over to the other side, and we typically put that in front of the plus or minus, mostly because anytime you write something after a square root, you run the risk of the square root looking like it went too far and is over the other things. So that's my best reason. I think it looks better that way. Our solution set is -4 with a plus and minus square root of 10. And it could be that, depending on your teacher, they might be picky and want you to separate those into 2 separate things, -4 plus square root of 10 and -4 minus square root of 10, but you'd have to ask your teacher specifically about that. It does say to use an exact answer, and so remember that square roots are exact, whereas if I type this into my calculator and get a decimal, I have to round, and that makes this less exact. So this is the answer I believe that it is looking for. Let's solve a radical equation. So radical. In order to get rid of a square root, we square. And actually, in the same way as what happened to us with our rational equation earlier, where I said that because we were multiplying by an x, that we were potentially introducing extra solutions, extraneous solutions into the mix, the same thing actually happens here. So we do have to do a double check at the end to make sure that our answer really is an answer. When I square the square root, I get 5x plus 4. And when I square x minus 4, it is not just x squared and plus 16, although that is a part of it, which I get that by doing x squared and -4 squared. There is also an inner term that comes because we are foiling out x minus 4 times x minus 4. Easy to forget about that, but whenever we do x times -4 and -4 times x, we get -4x twice, so that's a -8x in the middle. And then we get everything on the same side. I know that's a horrible looking 8x, but I'm just going to run with it while I sit here. We subtract both of these over. Again, it's easier to solve quadratic equations whenever they have a positive x squared, so that's why I chose this direction. Also, it meant there were fewer things to move, so it was overall a pretty convenient thing to do. Let's see if we can factor this. Is there anything that multiplies to get a positive 12 that adds to get us a -13? Just realized I don't need those headphones on. The answer is yes, -12 and -1. So we'd say, well, what makes these 0 in order to finish solving? So that means that we get positive 12 and positive 1. Okay, I'm going back through and checking the answers here, and I actually, later on as I was doing this in the video, I realized I did not actually check these answers to see if they were both correct, even though I've probably just gone over the idea of extraneous solutions. So an extraneous solution would happen here if when I plug in either 12 or 1, I get something that's not true, and it would happen because we'd get something that square roots to get a positive value, whereas this side could give us a negative value. What I mean by that is check out what happens when I put in 1. 1 minus 4 is -3. But if I square root 5 times 1 plus 4, which is square root of 9, I don't get -3, I get +3. And so 1 is actually an extraneous solution here. 12 is fine because you work out 12 and you get square root of 64, which is 8. You 12 minus 4, which is 8. And so that works, but the 1 does not work, so sorry about that. And that looks like the end of a section there where we had a bunch of equations of different types to solve. This is still a little related though, because it says compute the discriminant, then determine the number and types of solutions of the given equation. So the discriminant is the part of the quadratic formula that is underneath the square root. And so by just finding that number, it will tell us whether there are real solutions, whether there are imaginary solutions, or if there is just one real solution. So normally in a quadratic equation we get 2 solutions, but there are times where we will just get 1 because we're basically getting the same one answer twice. That whenever I factor and get things like x minus 2 times x minus 2, so I'm getting the same thing twice, that's a repeated solution, but we only have one answer, 2. We don't say it's 2 and 2. But the other situations are that we could have 2 real numbers as answers, or we could have 2 imaginary numbers as answers. I suppose we could have an infinite number of real solutions. I don't feel like that is something the discriminant tells us, though. I'm not actually sure how that would happen. I think actually, no. You would have to actually be trying to like get everything on one side, and all of a sudden your x squared and your x would have to cancel, and you'd have to get something like 0 equals 0 or 5 equals 5 or something, and that would mean that there were actually a whole lot of solutions that could have been true. But the discriminant wouldn't actually help us with that. So remember that these numbers a, b, and c come from what's in front of x squared, what's in front of x, and the number itself at the end. So b squared, I'm going to do -3 squared, a is 1, and c is -5. So -3 squared is 9, -4 times 1 is -4, -4 times -5 is +20. So the discriminant is 29. It says simplify your answer. I guess it didn't want us to just like have it written out and not actually find the number. When you get a positive number for your discriminant, that means there are 2 real solutions. When you get a negative number for your discriminant, that would mean you're trying to square root a negative. That would give you 2 imaginary solutions. If you were to get 0, then square rooting 0 means that plus or minus in the quadratic formula didn't actually need to be there. So that's when you get 1 real solution. So because we got positive 29, we would have 2 unequal real solutions. And we don't know what they are. They didn't ask us to solve it all the way, but we do know that there are 2 real solutions. Oh, words. Words are great. I'm just kidding. Words are awesome. No, it really, word problems are just, they're tough until you get them, you know? Like, once you've seen enough of a certain type of word problem, they're not so bad, but it does take some practice to get there. So, after a 90% reduction, you purchase a new sofa on sale for $72. Who sells a sofa for $72? That's not even an IKEA sofa. Okay, what was the original price of the sofa? So here's how, oh, a 90% reduction, that's why. There must be something really wrong with it. So they basically, we started off with the price of the sofa, and then they said, take 90% off of that price. So what's left if you take off 90% of the price? 10%, right? So what we end up paying is actually 10%. I have confused myself on how I wanted to write this. We are taking 10% of the original price, and that's giving us 72. So what we need to do is actually 72 divided by 0.10. And in general, whenever you have a problem like this that you know the end result and you're trying to go backwards, you're going to end up dividing. So let me just do this real quick. 720. See, that's the price of a sofa. I want a sofa that's 90% off. That sounds like a great idea. A new word problem. A rectangular athletic field is twice as long as it is wide. If the perimeter of the athletic field is 360 yards, what are its dimensions? It's talking about a rectangle. So let's draw a rectangle. So in general, length is usually the longer side and width is usually the shorter side. When you are finding perimeter, you end up doing length plus width plus width. That they're telling us equals 360 yards. But they've also told us that it's twice as long as it is wide, which means that instead of having to write a separate variable here of L and L, we could say what the length is with respect to the width. In other words, each length is 2 widths. And that's helpful because now, when I add all my sides together, W plus 2W plus 2W, now I only have one variable, so I can actually solve and figure out what the width is. 1 plus 1 plus 2 plus 2 is 6W. So I divide both sides by 6, and I get that W equals 60. So the width is 60 yards, and then we just have to think, okay, well, if the length is twice the width, then that should be 2 times 60, which is 120. That's a really common type of problem to see, so definitely one that you want to try to get used to seeing and understanding how to follow through with. 35. A tree is supported by a wire anchored in the ground 24 feet from its base. The wire is 18 feet longer than the height that it reaches on the tree. Find the length of the wire. Let's see. We have a tree. Look at that wonderful tree. We have a wire. The wire's a little better. But we're assuming that the tree makes a, well, are we? It's anchored in the ground 24 feet from its base. The wire is 18 feet longer than the height that it reaches on the tree. So whatever this height is right here, the wire is 18 feet longer than that. So it's h plus 18. Find the length of the wire. Now, I think we have to assume that this is a right triangle, otherwise I think we're stuck, because if it's a right triangle, then we can use the Pythagorean theorem. And I guess we should, since there's a wire involved, I mean, it better be making it stand up straight, right? Otherwise, what was the point of the wire, I guess? So the Pythagorean theorem is going to say a squared plus b squared equals c squared. So 24 squared plus h squared equals h plus 18 squared. So we do need to FOIL out h plus 18, and we do need to figure out what 24 squared is, which I don't quite have memorized, so I'm just going to do that on my handy calculator real quick. That's 576. That's h squared. When I FOIL out h plus 18, I'll get h squared plus h and 18 go together to get 18h, and that happens twice, so that's 36h. And then 18 squared is 324 is my guess that I'm going to double check. 324 is the answer. So then at first, since there is an h squared, my first thing would be to try to get everything on one side, but as soon as you start to do that, you should see the h squareds cancel out. So then our goal is to actually get the h by itself on one side with everything else on the other. If the h squareds didn't go away, we would have to do a quadratic formula or factoring situation. Let's subtract these. 252 equals 36h, divide by 36. Does this divide evenly? It does 7 times, so h is 7. Unless, it says other than no solution. That's what, remember I said that, the circle with the line through it means. So it's saying, other than that, use interval notation to express the solution set and graph the solution set on a number line. And the reason it's saying it that way is that if we do get no solution, then we cannot write our answer in interval notation, and we cannot graph our solution. It would be just a blank graph. So we want to solve this and see what happens, see if we can graph it and write it in interval notation. So I'm going to subtract 3x from both sides and get 3x. I'm going to add 14 on both sides. 3x is less than or equal to negative 1. I'm going to divide both sides by 3 and get x is less than or equal to negative 1/3. If you're thinking, ooh, there's a thing that I have to remember about inequalities. What is the thing I have to remember about inequalities? It is that when you multiply or divide by a negative number, you have to flip the inequality around. That's not what we did here. The negative 1 was on top, not on bottom. If I divide by a negative 3, yes, we'd have to flip it. But we divided by a positive 3, so we're good. This is not no solution, so there is a solution set. Interval notation is the one where you use parentheses and brackets. If x is less than or equal to negative 1/3, that means our answers are anything from negative infinity to negative 1/3, and since we are equal to, we'd put a bracket. Parentheses means not equal to, and infinity and negative infinity always get parentheses because you can't be equal to infinity or negative infinity, or at least that's what I always say. All right, so this is being shaded to the left of negative 1/3 and needs a bracket, and the only one that looks even close to that is D. So sometimes you'll see it with the brackets or parentheses here on the graph. The other way is to have either a filled in circle on the number or an open circle on the number to show not equal to or equal to. So that's another option. An absolute value inequality. So earlier we had an absolute value equation. The only thing that's different for an absolute value inequality is that we are going to do an extra step of when we figure out what's going on with negative 18, we flip the inequality. And it's for similar reasons to why we flip the inequality, because we're dividing by a negative in an equation. It has to do with that we're taking what's on the left and we're saying, what if it's positive? And then we're taking it and saying, what if it's negative? But our first step can be to just move the negative over to the other side. That's what's making it be negative 18. That's what's going to make it flip to be the other direction. So I'm going to write this down twice and solve. Less than or equal to 18. And then we're going to write it a second time, but we'll put greater than or equal to, and we'll put negative 18. So in both of these, I'm going to have to distribute the 4 and add 10. So that'll be 4x minus 4, but minus 4 plus 10 is plus 6. And I'm going to go ahead and that's going to be the same thing on both of these. The same steps actually happen. It's that because one is a positive and one is a negative, you'll end up with different numbers at this point where we subtract 6. So 4x is less than or equal to 12, so we divide by 4 and get x is less than or equal to 3. We subtract 6 on this side. 4x is greater than or equal to negative 24. Divide by 4, divide by 4. X is greater than or equal to negative 6. So if I kind of rearrange this, it's saying that we're bigger than negative 6 and we are less than 3. And I know it's an and because these are headed towards each other, right? If we go this way from negative 6 and this way from 3, hopefully those are the correct directions, then they're headed towards each other. So we've got this middle section of a graph that's going to be our solution set. They're both going to be brackets since they're both equal to, so we do negative 6 comma 3 bracket bracket, and that's our answer. Ooh, let's find the slope. So there's a formula for that, y2 minus y1 over x2 minus x1, or if you just remember, I'm going to subtract the y's on top and I'm going to subtract the x's on bottom. And since I'm subtracting a negative 4, that makes a positive 4. So if you can just remember subtract them, y on top, x on bottom, then that is how this works. 4/8 simplifies to be 1/2, so the slope is 1/2. Now it also asks us if this means that the line through the point rises, falls, is horizontal, or is vertical. Because we got 1/2, it's not horizontal or vertical. Horizontal lines have 0 slope, because they would be 0 fun to ski on. Vertical lines have an undefined slope because you would have an undefined amount of fun skiing on a slope that goes straight down forever and ever and ever. Don't read too much into that analogy. But rises is meaning rises to the right, falls is meaning falls to the right, that we look from left to right, just like how we read. And actually it says that in those choices, so that's helpful. So a positive slope rises and a negative slope falls. So that means that this line rises from left to right because it's a positive 1/2. Well, this is a long problem that I don't even know, I can't even quite get all of it in one screen, so might have to scroll at some point. Use the graph to determine the function's domain, the function's range, the x-intercepts if any, the y-intercept if any, and the missing function values indicated by the question marks below. Okay, we can do this like so. Okay, so domain is x values, and the issue with domain happens whenever your graph basically has a boundary on the left or the right or some point in the middle where it skips over. And so this is a parabola. That's not happening. We could go to the left forever and get an answer if we could zoom out on our graph. We could go to the right forever and get an answer. There's not an x you can think of that wouldn't give us an answer for this, or at least not a real x that we couldn't get an answer for. So the domain is all real numbers in interval notation. That is -infinity, positive infinity. If you haven't already been told this, interval notation, I think, is the most likely one you'll see being asked for in pre-calculus and calculus and beyond. It's my personal favorite. Maybe that's because that's the one that I kept being asked to use, but I also just think it's the easiest one to write, and the shortest one to write. Range is y values, so up and down. The range on this is not all real numbers, because if you look at the graph, there is a bottommost point to our graph, which means that all of the values below that bottommost point don't happen in the range of our function. So if I look, that looks like a -1 for y is my lowest point. So I would write my range as -1, infinity with a bracket around -1 because it does look like it's touching -1. They'd have to be pretty obvious, I think, if it was not touching -1. So if we have an asymptote, it wouldn't be touching, or if it had an open circle drawn, it wouldn't be touching, but this looks like it touches. And what I know about parabolas also suggests that it probably touches. So we'd say -infinity, no, we won't say -infinity. We'll say -1, infinity with a bracket around -1. Okay, x-intercepts and y-intercepts after that. So the x-intercepts are where it goes through the x-axis. So here at 1 and -1, the x-intercepts are -1 and +1. Well, that was a really bad job filling in that circle. Is there a y-intercept? Yes. That's where it goes through the y-axis down here at -1. And then part E asks us to identify these function values. So when it says f parentheses -2, it's saying f of -2, and it's saying what is the value, or what is the function when x is -2. So you look at the x value of -2, you follow -2 up until you get to the graph, and you say, oh, that's a function value of 3. So I'd write down 3. And then for +2, because this is a parabola and because of where our symmetry is, it actually would also be 3. So that's how we walk through each of those things looking at a graph. We're moving right along here. So this is asking us, it gives us an f of x and a g of x, and it asks us first to find g of 2, and then to find f of g of 2. This is called composition of functions whenever we do the second one. And there's another way that they write it, f with a small but open circle, which is not something that is obvious here that that's an open circle. This is another way we could write it. I don't know if this is a universal thing, but I remember we used to call it fog, or another way, goth. But that's not, it's not really named that. It's f of g or f or g of f or whatever. Anyway, so first on this one, let's plug in 2 for g. So g of 2 equals 6 times 2 minus 3. So 6 times 2 is 12. 12 minus 3 is 9. That means g of 2 is 9. Now here's what's neat about the way they asked us this. They want g of 2, which is 9. Now they want f of g of 2. So if they just wanted f of g of x, we'd take g of x and we'd plug it in for all of the x's. But they want us to do that, but also plugging in 2, and we've already found the answer to that. If we do f of g of 2, we're really doing f of 9, which is actually a lot easier than if they had asked us f of g of x. Because if they asked us f of g of x, we'd have to square 6x minus 3 and add like terms and stuff like that. But we don't have to, because they helped us out here. What we need to do is 9 squared minus 9 minus 4. So 81 minus 9 minus 4. So 81 minus 9 is 72. 72 minus 4 is 68. So there you go. Some slope again. Point slope and slope intercept form. So let me remind you, the slope intercept form is y equals mx plus b. Chances are that was like embedded in your brain at some point by a math teacher. And if not, where have you been? Just kidding. You're fine. Point slope is one that looks a little weirder, but I think the majority of the math community that does math at a higher level thinks point slope is infinitely more useful than slope intercept form. So just keep that in mind, that you'll probably be using point slope as much, if not more, than slope intercept form. So we have an x1 and a y1 and an x2 and a y2, and we need to find the slope. So we need to subtract our y's over our x's, which gives me 14 over 10, which simplifies to be 7 over 5. So our point slope, that's why this is why I like point slope. We can pick whichever one of these points we want, and I'll write both of them for you just so you can see how that works. But we get to just leave it without distributing, without solving for anything. So with our first point, we'd write y plus 3, because of its minus minus, equals 7/5, and then x plus 5. Or the other point gives us y minus 11 equals 7 over 5 x minus 5. And then the slope-intercept form, we could use our slope and one of the 2 points and plug it into y equals mx plus b and solve for b. But since we already have this in point slope, we could just take one of these and distribute and solve for y. And basically that's doing the same thing as if you were to plug it all in and solve for b. So I'm going to do it on the second one, just for funsies. I don't have a good reason for doing it on the second one instead of the first one. 7/5 times x is 7/5 x. 7/5 times -5, the 5's would cancel, so I'd have 7 times -1, which is -7. Finish by adding 11 over, and you get y equals 7/5 x plus 4. Voila! Ta-da! Not so bad. Given the slope and y-intercept of the line whose equation is, give the slope and y-intercept of the line whose equation is given, then graph the linear function. So this is in slope-intercept. The slope is the number in front of x, which is -2/5. The y-intercept is the number that's being added or subtracted, so that's 5. Over here we have this lovely looking graph. We start or begin with the y-intercept. Begin starts with b, and in y equals mx plus b. The y-intercept is b. So we begin at 5, and then we do our slope. -2/5, you either put the negative on top or bottom, but not both, because if they were both negative, they would cancel and give us a positive. So I need to go down 2 and right, which is positive 5, or up 2 and left 5. And notice that it's a negative slope, and so it falls to the right. Drawing lines on a writing tablet, for me at least, is super tricky. So this is actually one of my better attempts at drawing a line. So you're welcome. Divide using long division. Yay. Everyone loves long division, right? And then vertex of a parabola. Okay, we can do this. We're getting there. So we set up long division by putting what we are dividing by outside and what we are dividing into on the inside. It's not going to be a super long problem since this is a trinomial, so that's something. So this is very similar in a lot of ways to how we do long division with numbers. It's just more complicated because there's x's. We say, how many times does 5x go into 15x squared? Or thinking of it another way, if I divide 15x squared and 5x, what do I get? I would get 3x. And I'm going to write that above this other x to keep track of how many more things I've got left in my problem. So once we figure that out, then we do both of these two things times 3x and subtract whatever we get for our result. So 5x times 3x is 15x squared, but we subtract it. Negative 4 times 3x is negative 12x, but we need to subtract it. Subtracting a negative makes it plus 12x. And that's the thing that I think trips us up most about polynomial long division, is remembering to change the sign when we write down that step. So now I start over and say, okay, how many times does 5x go into 5x? And that is just one time. So I do 5x times 1 and get 5x, but I subtract it. Negative 4 times 1 is negative 4, but I subtract it, which is a plus 4. And so those cancel. I get 1 for my remainder. So this is, I was making sure I knew. So that is, I got confused about which way I should write this, but now I'm good. This is 3x plus 1 plus 1 over 5x minus 4, because our remainder we can write as a fraction. That happens in regular long division too. Back before we realized, oh, we could make it decimals and decimals and decimals, we either wrote remainder and just said, hey, the remainder is this, or we wrote it as a fraction, so that we have like a mixed number like this. In the following exercise, find the coordinates of the vertex of the parabola defined by the given quadratic function. There are two options here. One is, do you know the vertex formula off the top of your head? And two is, can you complete the square on this so that you will have put it into vertex form? Of those two things, I think it's easier just to attempt to have the vertex formula memorized. It's negative b over 2a. It happens to be the beginning of the quadratic formula and the bottom of the quadratic formula. So if you find negative b over 2a, that's going to give us the x part of the vertex, and then we just plug it in and get the y part. So this is b and this is a. So negative 16 over 2 times 4, negative 16 over 8 is negative 2. That's our x. And then we plug in negative 2. Negative 2 squared is 4. 4 times 4 is 16. 16 times negative 2 is negative 32. 16 minus 32 is negative 16. Plus 3 is negative 13. So there's our answer, negative 2 comma negative 13. Okay, use the vertex and intercepts to sketch the graph of the quadratic function. Give the equation of the parabola's axis of symmetry. Use the parabola to identify the function's domain and range. Now this is written a little bit misleadingly. Normally I would see this 16 as a plus 16 at the back, because now this is vertex form. In vertex form, we look at the number inside and we do the opposite. So the x value of this vertex is positive 1. We take the outside number, the plus 16, and that gives us the y value. And we don't change the sign there. Inside parentheses, you change the sign. Outside parentheses, you don't change the sign. That negative in front is telling us that this opens down. And since it's a -1, there's not a vertical stretch or shrink happening. It's just going to do a normal square pattern of going down 1, out 1, down 4, out 2, down 9, out 3, down 16, out 4, all of those related to perfect squares. So I'm going to start at 1, 16, and then go down 1, out 1, and then it says use vertex and intercepts, and I don't know that I agree that that's the easiest way to do it personally. I'm a big fan of graphing using transformations. So out 3 and down 9, so that would be here. Down 16, conveniently enough, out 4. I don't want to connect these because I think I'm going to make this look way worse when I connect them. Maybe if I practice enough, I'll get better at this. Okay, look at that beautiful parabola. Just want to take that parabola and put it on the refrigerator for everybody to see. The axis of symmetry is the vertical line that divides this in half so that you see the same thing on either side, kind of like a mirror. So that would be x equals 1, because vertical lines are x equals lines. The function's domain, well, parabolas don't have any issues with x's. You can plug in anything you want for x and get an answer. So the domain in interval notation is -infinity, positive infinity. The range is being limited by the fact that there is a topmost point of this, the vertex. So because the highest y value I can get is 16, I would write the range as -infinity, 16 with a bracket around the 16. Okay, varies directly is in this next word problem, and so we want to set up an equation that works for this. So when something varies directly, the opposite of that is varying indirectly. And so varying directly means that when we write this, we won't have a fraction, whereas when we vary indirectly, we would put a fraction. So we have the number of houses that can be served by a water pipe. I'm going to use N for number of houses. Varies directly as the square of the diameter of the pipe. It's important that we put the squared with the diameter, otherwise we get this wrong and do the whole thing and then look at the answer key and spend 10 minutes trying to figure out why it's wrong. Not that I know anything about that or anything. So we need something else here, which is our constant of variation, to help us know what the relationship to this is. So this is saying that as the number of houses gets bigger, the size of the diameter of our water pipe also needs to get bigger in kind of a direct way, as opposed to indirectly would mean we'd put the d squared on the bottom of a fraction and k would still be on top. And in that relationship, it would mean that the diameter was actually getting smaller as we needed to put water to more houses, which doesn't make sense as far as what I know about water supply. Now they're giving us information here so that we can figure out what K is. If it's a 10 centimeter diameter, we put 10 right here where D is, and it's 40 houses, so that goes here. And we solve this. 10 squared is 100. We divide the 100 over, and we get that K is 40 over 100, which simplifies to be 2/5. And then I can rewrite that so that I can now use my equation for these two problems that ask me. A water pipe that has a 40 centimeter diameter can supply how many houses? So we would square 40 and then times it by 2/5. So 40 times 40 is 1600. And 1600 times 2/5, well, if I divide it by 5, I get 320. And 320 times 2 is 640. So that would be 640 houses. And then for this next one, it's N that we know, and it's D we're trying to find. Whoops. So we would divide both sides by the 2/5, which is the same as multiplying it by 5/2. And then we would have to square root our answer. So let's see. I'm not going to do this in my head. I'm going to go get my calculator. Calculatora, where are you? It's on my screen over here. Okay. 1440 times 5 divided by 2 equals 3600, the square root of which is 60. So it would take a 60 centimeter diameter so that we could supply all those houses. 47. Solve for x. So there are two ways to do this. One is to use logarithms, and one is to attempt to write 2401 as 7 to some power. And if 2401 happens to be 7 to a power, then that's the easier way to go. Now, fortunately, whenever we're talking about powers, they get big really quickly. So I know that 7 squared is 49, and I'm pretty sure 7 cubed is 243. No, 343. If I times that by 7 again, which would be 7 to the 4th power, I get 2401. So, if I can do that, if I can rewrite 2401 as 7 to the 4th power, there's this cool thing we can do. We can say, if we have 7 to this power equals 7 to this power, don't their powers have to equal each other? And we just get rid of the bases. We say, check you later. We don't need you. So I'd add 8 to both sides and get 4x equals 12, and then divide by 4 and get x equals 3. If we were to use logarithms, we would rearrange this into a logarithm and use our calculator, or take a logarithm on both sides, rearrange and use our calculator potentially. But this is where, if you realize, oh, if I could just make this be 7 to some power, and you take the time to check to see if you can be really helpful. But the only way to figure out if it is 7 to some power is to guess and check like that I did. 7 squared, 7 cubed, 7 to the 4th, and I got it. If it hadn't worked, then by the time I got to 7 to the 5th power, right, I would have known that it wasn't 7 to some power, and then I would have used logarithms instead. But since you do logarithms in Algebra 2 and pre-calculus, and in pre-calculus, you usually treat it almost as though you didn't do it in Algebra 2, depending on your teacher. You shouldn't worry too much about logarithms right now, in my opinion. 48. Oh, look at this nice picture. To find the distance across a lake, a surveyor took the measurements in the figure shown. Use these measurements to determine how far it is across the lake. So this looks like a trig problem. Using a trigonometric function, because we've got a right triangle. So from this angle 44 degrees, A is the opposite side and 680 is the adjacent side. And if you memorized how to do sine, cosine, and tangent the same way I did with SOHCAHTOA, then you'd say opposite and adjacent go with tangent. So tangent of 44 degrees equals A over 680. So we would multiply both sides by 680. And I am going to have to do this on the calculator. On your calculator, you want to make sure you're in degree mode. And if you're doing it on your phone, you'll want to type in 44 and then tangent, and it should give you something like 0.965688, blah, 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 and then times that number by 680. If you have a nice handy-dandy graphing calculator, you would be able to type it in all at once. But either way, make sure you're in degree mode. I get 656. Oh, I'm supposed to round to the nearest whole number. So that goes up to 7. 657 yards. Okay, two more problems. All right, use these two things to find the rest of the parts of this right triangle. So we know A is 28.6 and C is 51.5. To find the third side, we could use the Pythagorean theorem, or we can use one of our trig functions. Once we know what A or B is, we do need to figure out what either A or B is at some point. If I want to know what A is, this is the opposite side and this is the hypotenuse, so I would use sine. sine of angle A, which is what we don't know, equals 28.6 over 51.5. Now, we do 28.6 divided by 51.5, and then we do the inverse sign to get A. And so on your calculator or phone or whatever, that's second, and then the sign button, and there's a little sign -1 that shows up. That's the inverse sign. So I'm using my computer's calculator. So 28.6 divided by 51.5 gives us a decimal, and now I'm going to do found it, inverse sign. So what are we rounding to? The nearest tenth, 33.7. We can just say, okay, well, 33.7 plus 90 plus whatever this is equals 180. So I just need to do 90, which is what's left over for these two angles, minus 33.7, and that will tell me what B is. So that'd be 56.3. And then, like I said, we could use the Pythagorean theorem, or we could use a trig function now that we know the angle to find B. In theory, it'd be best to use the Pythagorean theorem, just because if we reuse one of the numbers we found and we got one of those numbers wrong, then that just makes our answer wrong as well. But if I at least am using the problem's numbers, then hopefully I could at least get one of the three right. So we need to do 51.6 squared minus 28.6 squared. Why did I write 6? It's 5. Getting 42.83. There's a chance that that's a little bit off because I did round the number before I square rooted, so sorry about that. Solve the system by the method of your choice. Now this is set up so that it'd be really easy to use substitution to take the 8y minus 1 and put it where the x is. But if you just really like elimination better, you can subtract the 8y over to the left side, and then you'll be set up for elimination. I think elimination is easier to remember, so I'm going to use substitution to remind you how that works. I'm going to put 8y minus 1, not there. That's not where it goes. It goes where the x is, because it's x equals. We get so used to solving for y, So -3 times 8y minus 1 plus 24y equals 3. That gives me -24y plus 3 plus 24y. Hang on a second. These cancel, and I get 3 equals 3. That is a special case. If 3 equals 3 is true, which it is, 3 does equal 3, that means that there are infinitely many solutions. So that is one of our options here. That's option B. And essentially the rest of this is saying, hey, there's infinitely many solutions. The solution set is anything that works for this system of equations, which is not a super helpful thing for them to have told us. If you have more complicated equations that give you infinitely many solutions, there are sometimes ways to make them easier, but this is not one of those cases. Thanks for watching. This has been a getting ready for pre-calculus video. You can see that there is a ton of stuff that it would be nice if you remembered if you're going into pre-calculus. And so after going through this whole thing, if you watch the whole thing especially, I don't even know how long it's going to end up being, because it literally feels like it's been all of my life that has taken up this time to make this. So you may be thinking, really, I have to remember all of this just to start pre-calculus well? And I would say, there's a silver lining. If you don't understand something that your pre-calculus or any math teacher is going over, stop them and say, in a polite way, stop them and say, okay, I'm confused about what you're talking about. Because sometimes it may not even be that you're forgetting a skill from Algebra 2. It could be that there was some, they made a mistake, or it could be that they just weren't clear. Other people might have the same question you're having, okay? But just ask them and say, hey, I don't get this. Or if they have made it apparent that, okay, we're going to work on this concept, and if you don't remember this from Algebra 2 or before, you're going to need to work on it. Well, there you go. That's your time to work on it. But otherwise, you don't necessarily need to go super far out of your way to have every single bit of all of these problems memorized. Going through this, though, hopefully will help you get back in the swing of things before school starts. And all of these are things that will come up at some point in pre-calculus. So it's not going to hurt you to remember how to do them ahead of time. But definitely check with your teacher as far as what they specifically are expecting you to remember, and just always being willing to say, hey, I don't get this, is helpful. Sometimes teachers don't respond well to that, but I think most of them do. You always ask me if you need some help. Just leave a comment, tell me what's going on, or check out my website, which is going to be in the description, and let me know if there's something I can do to help. So thanks so much for watching. Please like, comment, and subscribe.